Okay, welcome back, everybody. So this lecture is called Conserved Surface Layer Integrals. And of course, you will get to know what this is in a minute. So are there any other questions any further questions from the last lecture? Maybe there's, so two questions came up during the break, which are maybe helpful to understand. So the first question is this. So basically, the definition of differentiable jets, which I had written down before, or even the linearized field equations, sort of depend on this measure rho. And this measure rho was a minimizer of the causal action principle. So the point, like the setting in which we're working right now is the following. We assume that we know one minimizer, and we then want to understand which sort of minimizers are present in a neighborhood of that minimizer. And this is exactly why we wonder about this jet V, or this family rho tau. This is basically going, sitting in one minimizer, which we assume known. So this whole procedure is not about finding this one minimizer. It would be nice to have a general procedure about to find a minimizer. However, since the whole setup has so many free, if you like, variables, it's only possible numerically in very restricted settings, but in general not so. It's not about finding this minimizer. In fact, for example, you could take this minimizer rho to be the Minkowski vacuum, which you've seen yesterday. And then it's really about sort of understanding the neighborhood by considering those families. So this could be, for example, one family rho tau tilde, and then maybe we have another one rho tau tilde tilde, like this. So it's really about sort of considering those families, and even additionally, only considering those families infinitesimally. That's basically the story in which this game takes place. Is there any other questions so far? Yes? Yes.
We can talk about smooth spins and so on.
Yes. Yeah.
Is it in general true or not?
So this set of operators F, which you've seen before, this is a manifold if you fix the trace to be constant, and if you take how was it again, maximal rank? Forgot it is in the paper. Do you remember, Felix? And even so how the other elements of the setting of causal Fermion systems, for example the constraints, fit into this framework, this is explained in a little section in this paper I wrote down. So have a look if you like, or come up and ask questions. Yes, other question?
Maybe this is a stupid question, but what do you want to understand by analyze? Do you already know what, have you already something in mind when you wish to analyze what these families, or do you say, okay, let's analyze it and look what we see?
So the idea, what one sort of had, the thing one has in mind is basically the continuum limit, which I will explain a little bit tomorrow, and Felix will say more things about that So basically the idea is, so we know one minimizer, this Minkowski vacuum, and there are other minimizers sort of close by, like intuitively speaking, which are then like described by other equations, for example by the Dirac equation with external potential coupled to field equations of a particular form. And this is what one would like to understand. At least so that's as far as I have. You want to add something? No, okay. Yeah. Yeah.
These other minimizers which are nearby, do they have then also all the same value
Of the action? So like in general, every minimizer has the same value for the action by definition of being a minimizer. It means, but we only like, basically we only look at extremal points. And so I don't know, yeah. Yeah. F? Yeah, so like we generally consider finite dimensional manifold, but it, so it could be non-compact, or it should be non-compact.
You always assume that the Hilbert space is finite.
Yeah.
Must also finite.
Yeah.
Something similar to a flat manifold. So it has a very high dimension, but it's finite.
Mm-hmm.
Does it not use a differential structure on because M is a subset?
So it's M is just an arbitrary closed subset. So therefore, like, it's not a differentiable manifold or differentiable submanifold. It could be, yes, yeah. Mm-hmm. It could, yeah.
I have also a stupid question.
Yeah.
How we know that the minimizer is really a minimizer and not a maximizer?
So in our case, we don't know that because the Euler-Lagrange equations are just like local extrema. So it could also be a maximum. Yeah, we don't know it. Yeah. So at least in this setting, we don't know it. Yeah.
So it could be maximizer.
Yeah, exactly. So I mean, so we basically, the Euler-Lagrange equations I've written down correspond to the first variations. And there's also something you can write down which corresponds to second variation. It's also in this paper which I wrote down. And the second variations then basically make sure that you have a local minimum and not a local maximum, but it's still local. Yeah. Mm-hmm.
Did you concern that how a minimizer and maximizer are related? Or can you imagine?
So
If, for example, if you have a potential, so wave potential, and you have minimum and maximum. Imagine you have one minimizer and one maximizer.
So here I would say like they're independent like this. I mean, there's no transformation which takes a minimizer and gives you a maximizer.
In field theory, there is
Yeah, could be. Yeah, here not. Yeah.
So if
Yeah.
you have an instant
Mm-hmm.
potential, tunnel potential, that relate one minimum to one maximum.
Okay. Yeah. So I mean, here it's different. Like, yeah. Okay. So let's see what we want to talk about in this lecture. So so remember that we had those two jet spaces which were relevant. The one was the space of test jets here. Oh, and sorry, one more thing I wanted to say about concerning understanding. So the thing we really look for in this linearized field equation is V. That's really to keep in mind. We look for a particular jet V. This will be a solution of this equation. It's the same thing as, like, you would consider the Dirac equation and you look for psi. In the same way you look for the V here, even so the V pops up in a different place, so to speak. Even so the V here is the direction in which you differentiate. You still look for V, a linearized solution. That's what you want to know. And in fact, what we'll do now is we will now consider jets U. Maybe let me just write. So U will always be A U, and jets V, and V will also always be BV, like just the scalar component, the vectorial component, and they are now linear solutions which are also differentiable jets. And so we are working with this subspace J-test, subspace of J-diff all the time, just because there are settings, for example, the continuum limit, as I will explain tomorrow, in which you just want to work with a subset of those. You don't want to consider all differentiable jets. And again, differentiable doesn't mean that the jet is always smooth anyway. It just means that the Lagrangian is differentiable in the corresponding direction of the vectorial component. And maybe just as a recap, so so before we've defined the derivative in direction of a jet for positive, like the right derivative, and now just as a recap, let me just write down the left derivative again, but this is really intended to just bring this formula up again. So applied to L, this would be the same as before, so we have A of x, L of x, and then we just have plus, and then we have du minus L of x, okay? It's the left derivative, the left directional derivative in the direction of a jet. And just a little bit of notation, which we'll need. So let's say S and S prime are just so either plus or minus, so either right semiderivative or left semiderivative. And then this formula here, u of x, and then let me just write it like this, 1v, and I have an s here, an s prime here, L of x and y. Well, this formula is just saying that this x here indicates that the u derivative, like du, acts also on v, okay? This is just a notation which we want to use in a minute. So if there's if there's two derivatives appearing and the first one has an x here, this indicates that it's just acting like this x here, this derivative acts on the v and on the x dependence of L. In contrast, if I would have something like nabla 1u s nabla 1v s prime L of x y, this would just mean that both of them are just acting on the L. It's just a fixed notation. There's no mathematics happening here. Okay. And we again need some assumptions, and let me just write them down real briefly because I will use them in a little proof in a minute. So the assumptions which we have this time are the following. So maybe I will abbreviate them a little bit. So the first one is first and second. So this is a second semiderivative, right? There's one and there's another one. First and second semiderivative of L exist. That's the first assumption which I need. The second assumption is second semiderivatives can be interchanged with row integration. So we can, semiderivative can be exchanged with row integration. And the last assumption is S2, and the last assumption, S3, basically says that for all u and v in this set of linear solutions, which are also differentiable jets, so in J-lin cap J-test, the following holds. We assume that the commutator of those, u, v, so that's uv, vu, is also in J-test. So that's what we need. Okay, and now with this we can basically take a look at a quantity which basically comes or appears. So maybe let me say it like this. So, since u and v are in the linearized solutions and in the test spaces, so we can anti-symmetrize the linear field equations in u and v. And this is what we'll do now. So what do we get if we do this? Well, So first of all, note that those assumptions here are only about semi-derivatives. So in general, I will just do this by color here. We'll just have to put semi-derivatives on all of this. Yeah, so let me just put S prime here. Okay? And S and S prime can now again be plus and minus. Okay, now we just consider first term in the linearized field equations. Is that a fire alarm? Okay. So consider the first term in the linearized field equations, okay? So I'm just going to write this term down. So this term looks like this, and anti-symmetrized. So I consider the first term anti-symmetrized. So how does this term look? Well, it looks like this. I have this integration of m. Now I use this assumption S2 to already put the first semi-derivative inside the integral. So I have something like this: u of x, using the notation I've just introduced, nabla s prime 1v minus nabla s prime v of x nabla s 1u. This is the first term of the linearized field equations. L of xy, the rho of y. Well, what I can do now is, maybe I'll write it down here. So what I can do now, I can now use a relation between the left and the right semi-derivative. So I've told you before that if I have the left semi-derivative, so for example, nabla plus is the same as, it works in both ways, minus nabla minus u minus, okay? I mean, if you think about this a little bit, so I'm just going in the other direction. So this is expressed by this minus u here. And then I get an additional minus sign by, because they're in the limit, like in the definition, there's this limit where tau goes from 0 from below. So this gives you another minus sign, and this is this minus sign. And this formula here, in general, you can express this formula like this. It's written like nabla 1v with respect to s is the same thing as s prime, nabla, and now I have 1, comma, s prime v, and then s prime here. So this just allows you, I mean, don't think too hard about this. So basically, I'm using this here. This just allows you to get those two semi-derivatives to agree. So what happens if I write it down is that I get something like this, s prime. This is true for all. Maybe I should write at least this. This is true for all s prime in plus and minus. And so if I apply this, I just get this quantity here. So this will be the integration of m. And what I'm left with is nabla 1, comma, s prime. And then I have the commutator of those two things. And I have a s here. And then applied this derivative in direction of the commutator applied to L of x, y, the rho of y. But now the last assumption here tells me that the commutator is in the test spaces. And the assumption, so maybe let me write it down. So assumption 6. What was 6? I don't remember, but it's. So assumption 6 allows me to take this semi-derivative out of the integral if this is in the test spaces. So basically this tells me that this thing looks as like this, s prime, nabla s, and then I have s prime u v. And now I'm left with this integration over L of xy. So this is just L of x plus nu half. And now I can again use this assumption S3. And this assumption S3 tells me, well, this is in the test space. So if that's in the test space, I can use the weak Euler Lagrange equations to conclude that this part here vanishes. So maybe we'll do it in 2 steps. So first I use assumption S3. to give me, so it's in a test space, so in particular, test space is a subset of the differentiable sets. So this means the derivative exists, so I can write it like this. So this is just the same as uv, and then the same thing in brackets, L of x plus nu half. Now I can finally use the weak Euler-Lagrange equations. And the weak Euler-Lagrange equations tell me, well, the derivative of L vanishes for all jets which are in the test space. This isn't a test space, so what's left over is just this, nabla u v times this constant nu half. But, so this is basically what we get from the first term. And this is the same contribution we get from the last term. This is the same as from the last term. Okay, so they cancel. Okay, and so the only thing which is really left over is the contribution from the second term. Left. So basically what I'm doing, we're proving a theorem, we're almost done. Left is contribution from second term. So how does this look? The second term of the linearized field equations. Well, this looks just like follows. So basically we have the linearized field equations imply that we have the integration over m, and then there's a quantity which is just getting a name, so I'm just going to call it sigma, subscript u and v to say that we're having those jets u and v, superscript s and s prime for this plus and minus of x, y, the rho of y is 0, so that's what we know for now. And with, what's this symbol I wrote down? With, and that's important now, with the sigma u v s s prime of x and y is just given as follows. So it's a semi-derivative with respect to u acting on the first variable, and then you see and a semi-derivative with respect to v acting on the second variable of L minus the same term just anti-symmetrized. So I have s prime 1v nabla s 2u, and this whole thing just applied to L of xy. And I'm just putting a box around this because this is important, yeah? Okay, now we just have to do 2 more steps, and then we'll see what we have found. So, yeah, so just fix any subset of f which is compact. So we'll call it omega, and then we integrate this quantity. So then we just, it follows directly that the integration over omega, and now, yeah, maybe let me write it this, integration over m, and then I have again sigma u v s s prime of x and y, and now the rho of x, that's the integration with respect to m, and the rho of y, this is the integration with respect to omega is 0. Okay, but sigma, let me write it like this maybe, but sigma of x and y, sigma u v s s prime of x and y is anti-symmetric in x and y. So you see it from the thing in the box here. So I'll give you some time to catch up. This is basically the last step of the proof anyway. So if I exchange x and y, so I know L is symmetric on the exchange of x and y, but basically this term here if I change x and y, this is becomes a second derivative, this becomes a first derivative, and those two things commute because they act on different variables of L. So therefore, this thing is just antisymmetric in x and y. And therefore, we know that the integration over omega twice of the sigma u v s prime of x and y d rho of x d rho of y is 0. Okay. And this means, and I now write this down in a nice theorem. So this means that we have basically found, so we can subtract this term, which is 0 anyway, from this equation. And let me just write down what we have found. And then I'll give you some time to catch up, and then we talk about what it is. Maybe let's do like this. I will write it down here real quick, because then I can give you some time to think about it before I clean the rest of the board. Okay, that is, what we have found is the following. The linearized field equation. And after this, there's a lot of pictures, so just bear with me a little bit more. Imply that the integration over omega, and now I have the integration over m here, but I know the part where I have omega here is 0. Yeah? By what I have just considered here. So what is left is really the integration over omega. Now I will just write the integration matter close to the integral because it's clearer, but it just means the same. So, and then I have m without omega, the rho of y, and then I have here the sigma u v x s prime of x y. Well, this is 0. Okay. And this is, okay. Yeah. Let me just put this in a little box, because this is an important sort of structure. And I will now explain you a little bit what this means, and then we'll write it down in a nice theorem. So while I clean the rest of the board, are there any questions so far? So what we've done basically is we've just considered the linearized field equations, as written in this blue box, and we just anti-symmetrized it, and basically without any real work, this sort of structure came out. This integration of omega with respect to x, integration of m without omega with respect to y. And this sort of structure is a structure which is called a surface layer integral. And this already appeared in the title of the lecture, which I just erased. And I will now explain in we'll take a lot of time to explain what this means and why this is an important structure. And we'll see later that what we found is something like, let's say, a symplectic form. What this is actually, maybe we could say the remains of a symplectic form. And if you would assume that everything is smooth, you would even find this is really like a symplectic form on the space of solutions of this theory. I'll say a little bit more about that, but no details. Okay, any questions so far? Yeah. So the reason why I say this is because if everything would be smooth, you could prove that it's antisymmetric, and in fact, it's really then a form on the tangent space of solutions. Like it's a real symplectic form in the sense of symplectic geometry, and you could prove that it's closed. And you can even mod out things of the tangent space to make it non-degenerate. But you're completely right, in this setting where the stuff is not smooth anymore, this is the only thing we have currently achieved. Maybe I don't know, like maybe there's a way to make more of the other, to capture more of the other structures, but you certainly would need more, you certainly would need to say more about what it means, for example, to have an exterior derivative in this non-smooth setting. And yeah. But I'll say more about this later. So right now, let's maybe just take a look to this sort of structure we have found here. Okay. Okay, so this is, so let's say, let's put a stop here. So we'll start the next sort of sentence. So this is a surface layer integral. Okay, what does this mean? Well, to explain what it means, suppose for the moment that L of xy is of short range. Okay, so what this means is, let me just maybe draw a picture first and then explain in words. So you already know, so let's assume we'll draw one of those space-time diagrams. So this is sort of, let me just say space, and this is sort of time. So this is also okay to draw those things in causal Fermion systems because we have a causal structure. And then basically the support, we already know that, so if this is sort of the light cone, we already know that the support of L, let's just say x comma dot. So we'll fix, let's just say 0 comma dot. Yeah, so we fix x to be 0. Let's just say this is our 0 for now. And then we just consider the rest. So we already know that the support of L is contained in this light cone. This is what Felix said yesterday, right? Because just the definition of causal structure and the definition of L imply that L vanishes if points are separated space-like. And of short range just means that there is some value, let's call it, this would be delta half. There's some value delta such that it's really 0 outside. So this would be, let's say, this is the support of rho as a string, the support of L of 0 comma dot if of short range. So I'm just saying this to explain things. Okay. And so just for the mathematical people, so this would just mean that there exists some Euclidean metric delta on F such that L of xy is 0 if x and y have a distance larger than delta. It's really just to explain.
But this is somehow compactification, because the time coordinate is not compact.
No, stop. It's not. I'm not saying something about the space-time. It's still non-compact, just about L. It just means the Lagrangian has a finite range. Okay. And so assume that this is the case. So maybe I write it. So maybe I said it. So that is, or maybe, is it clear what I mean with short range? Yes, okay. Okay, so let's see what this surface layer integral would imply in this case. So let's assume for now that the blackboard is just a set F. So we'll put a blue line here because it's a new picture which I'm drawing. Okay. Let's assume that, so we've talked about some set omega, so let's just assume this set omega has, I mean, it can have arbitrary form, right? So let's assume this is our set omega. Now, if L of is of short range, so is, maybe I should write this down here, L of short range so is sigma u v s prime of xy. Why? Well, this basically consists of derivatives of L. So if L is 0 at a certain, like if L is 0 for certain x and y, the derivative also needs to be 0. So basically what happens is, I have this set omega here, and now we look at this integral. So first of all, there's this first part of the integral. So this means I need to pick an x in omega. So x could be here, this could be a possible x could be, maybe let's do it like this, or it could be here, or it could be here, anywhere, yeah? And then I look at the second part of this integral. This is this part. This is y. Well, y needs to be outside of omega. So the y could be here, or it could be here, or it could be here. Okay? But now if L of is of short range, and x needs to be inside omega, and y needs to be outside of omega, it follows immediately that x needs to be in a strip of width delta. So this is basically where x can be. Let me maybe put it like this. Because otherwise there cannot be a contribution because the distance to y is larger. And in fact, so this would be, maybe I will just write it like this. So this would be delta. And the same thing holds for y. So if x needs to be in omega, there can be at most a strip of width delta in which y needs to be. Okay, so this is the possible spaces of y. So what you see is basically that, so the first thing we see, like from the illustration, just means like look at the illustration and you see that the integration is an integration over a surface layer. Surface layer. Yeah, so it's not over a surface, but it's over a surface layer. So basically, you take the surface of omega and you make it thicker. In general, I mean, this omega will be a subset of this space F, which has a high dimension. So you better imagine it in sort of higher dimensional form, but it's still the same thing. And that's why we call it surface layer integral. Surface layer of thickness delta or 2 delta. Delta, if delta is this short. Mm-hmm. So this, just stopped off short range. I mean, this is like informally a little bit. It's just to motivate. And I'll say more about this later, but those surface layer integrals really give surface integrals in the limit. At least in certain cases where we understood it so far. Okay, and in fact, surface layer integrals correspond to conserved quantities. In fact, describe conserved quantities. So how does this work? It works as follows. So assume we have, so we'll have to assume that we have some sort of structure like Minkowski space, roughly speaking. So maybe just, I'll write it in words. So let's assume we're in a situation where this is N1, this is N2, and the whole blackboard is M. So it's going to be like 3 pictures next to each other. So the whole blackboard is now M. It's a subset of F. And we'll just assume that N1 and N2 are N1, N2 are something like hypersurfaces, space-like hypersurfaces. Okay? And so what we can do now, well, we can now just pick this omega like this, right? And if we pick this omega like this, well, what we get is just what we have discussed. We'll get some, so a surface layer integral is some integration over this thing, of a layer around this omega. But note, the surface layer integral is 0. This is really important. So it vanishes. So we know that all of those 4 parts add up, and together they vanish. And what we can do now, we can now take those 2 lines here and send them further out to infinity. So for example, in the next picture, we would already have here N1 and N2. And we would still have the omega, but now the omega is larger, okay? And right now, so the idea which I'm explaining informally here is that if you send this out to infinity, the contribution of this thing might vanish. Of the contribution of those two parts of the boundary might vanish. So in this case, we made it a little bit larger, so we still have the integration over here, and we have the integration over here, and we still have an integration over here. So this is just to basically sort of describe with pictures a compact exhaustion of this area. And then finally, we would have a situation like this, where we have the n1 here, and where we have the n2 here. And so this is still going out to infinity. And finally, we would have basically just an integration over those two parts. And now the point is that, maybe I'll make another blackboard for this drawing. So the point is that if the integration over omega, the rho of x, integration m over omega, the rho of y, of this quantity is 0, then it follows that, let me just call this star, and star just means that those two contributions are equal up to a sign, okay? So just to summarize again, the picture which I'm trying to explain here in a little bit intuitive level is that I have those surface layer integral, they vanish. Now I consider two hypersurfaces, and I just let this boundary here go to infinity. And if it does not contribute at infinity, which is the case in some nice situations, so what ends up after taking the limit is just an integration over this hypersurface and just an integration over this hypersurface. And they and this and both together need to be 0, and that means they're the same. So this is like on level right now, it's an assumption. It's the same thing as saying like if I have wave function with compact support.
Because omega is oriented surface.
No, I don't think it's related to that. No, so it could be, but.
Oriented with that contribution from the both sides.
Mm-hmm.
Still the two sides, upper and lower, up to minus are the same.
So yeah, maybe. So, but the only thing I can say, like even if omega were oriented, it does not immediately follow that this contribution needs to go to 0. This is like really sort of an additional assumption.
You can write the surface integral as product of the line integral.
So I don't know. Yeah.
Okay.
Yeah. Yeah. Okay. And maybe let me explain this last part a little bit more. Are there any questions so far while I clean the blackboard? Sorry?
What is star?
Oh, star. Oh, yeah. Sorry, I meant this equal sign here. This follows. So it follows that basically, yeah. Okay, let me clean the board. So what this little calculation, which I'm just about to erase, shows us is that, is that from the linearist field equations, by manipulating them a little bit, we basically obtain a conserved quantity. And after just explaining this a little bit more, on an intuitive level, I'll just write it down as a theorem, what we have found. Maybe it makes more sense to write it down as a theorem first. Okay, or maybe let's just try it like this. So basically, the conserved quantity is is the following. So it's basically, like still in this, speaking in this a little bit intuitive language, is basically just the surface layer integral where I put omega, and let me just put an omega n, for example, 1 here and I here. So this is just one of those hypersurfaces, the rho of x, integral omega m without omega ni, dy of x, and then just, I'm putting dots here because we have found one expression, but there are others. I'll talk some more about this later. So this is the conserved quantity where omega ni is, let me maybe write it like this, is the causal past, or the past light cone or something like this, of this Cauchy surface Ni. So this is like the past of Ni. So just to give to draw it again as a picture, so this just would mean if this is my Ni, this omega Ni would really be the causal past. Okay, and if I define it in this way, then this is really this quantity which is conserved by the vanishing of this surface layer integral. And of course, like in applications, you have to check that this is well defined. And what did I want to say about this? Yeah, okay, it seems like this is what I wanted to say. Okay, yeah?
This vanishing has any consequence of this surface?
So this is the point. Like, if I have such an so the whole point of this informal things I have just said is whenever I have an integral which has this structure, so basically integration omega, integration m without omega, and then something with L, then this is basically the indication of the existence of a conserved quantity in this framework. And in fact, I'll say something later about it if we have time, and if not, we also prepared an exercise about this. So the point is, it can really be shown that for a particular type of conserved quantities, which generalize Noether theorems, in the limit, this gives, for example, Dirac conservation of energy momentum and conservation of current in this integral form. So not in the not in the differential equation form, but in the integral form. This is, yeah.
This is my point.
Yeah.
A conserved quantity, maybe this conserved quantity corresponds to some minimal surface.
Yeah. So I don't know. Sorry, but we can discuss it later. So I mean, I would have to ask now in more detail what sort of surface in which space, but I think this leads us too far away. Let's discuss it after the talk. Yeah.
So I mean, the Lagrangian being of short range.
Yeah.
Is that a necessary condition for this other quantity, whatever you find to be of short range? And secondly, is that a kind of a generic condition that actually does pop up, or is that kind of technical?
So so in this, so for now, it's just an assumption to really make it like plausible what's happening. But so what happens is that in the continuum limit, the real Lagrangian of the theory has certain fall-off conditions to different orders on the light cone. This will pop up a little bit tomorrow. And this is like the corresponding sort of thing to that. Or Felix, do you want to add something?
Well, it decays like on the kind of Compton scale. So it's L of x mark in the continuum. So therefore then basically the size of this strip will be something like 1 over the mass of the electrons in the particle. Well, this is for most of the cases, this is
Yeah.
reasonably short.
Yeah. But yeah, exactly. But just yeah. So it's not like exactly equal to 0, but it has this decay property.
And here is kind of strict short range. This is just a perfectly nice idea.
Yeah.
So it doesn't really matter how fast it falls off.
But can you have when the Lagrangian is not of short range still construct something of short range from it?
So even in the case where the Lagrangian is not strictly of short range, like this is the case we considered to study the limiting case. And then you really do get the surface layer integrals in those cases I've mentioned.
But if the L does not decay, it's not of short range, then everything still works, but it's no longer like a kind of a quality
Okay, so in summary, what we have found with this calculation before so above, this relates to the equation before, we have found a conserved quantity. Or maybe the better word would be, we have found that which we call conserved quantity in the theory for particular reasons. And I'll just write it down as a theorem, and you've basically seen the proof as follows. For any compact, oh, and one thing I wanted to say before I continue. So in this picture, you see why it's necessary that F, and in particular the closed subset of F, M, the spacetime, is non-compact. Because if spacetime were compact, the past of this hypersurface would be compact as well, so we would immediately know that this thing is identically zero. So it's important that it's not compact. So for any compact omega subset F, the surface layer integral okay, how does it look? Well, so basically we'll call it like this. Sigma, we'll just put an omega here. So it takes a chat in J lin cap J test times, so with another chat in J lin cap J test to the real numbers. And basically how it works is it takes a u and it takes a v and it maps it to integration over omega, the rho of x, integration of m without omega, the rho of y, and then I'm just going to sum over those semi-derivatives which we still had before. So 1/4, and I have to sum over s prime, they're plus or minus, and then I'm just going to have this u v s prime of x and y. So, and this term here is as before. So I had that in the box. And this just satisfies sigma omega of u and v is equal to 0. Okay, and this vanishing here really, in this context, is the thing, the reason for calling this a symplectic form. And in fact, so maybe I could add this here. It is bilinear and antisymmetric. Okay, so bilinearity basically follows from one of the assumptions we had before. Okay, and this is basically the end of the theorem. And now just a couple of remarks, some of which I had said before. So remarks about this, and then we'll see some other conserved quantity. So assume smoothness, and I'm just going to leave it like this. So assume smoothness of the Lagrangian and this little l, and you assume that the manifold of solutions is smooth, and so forth. And then it really follows that this sigma is a closed two-form on Fréchet manifold of solutions of the solutions of the weak Euler-Lagrange equations. So this is like a presymplectic form. And in fact, what you can do is you can then, like still assuming this, mod out parts. So this would be called B. Mod out parts of T rho B. So that's the tangent space at a minimizer of this Frichet manifold. And then you can even have like non-degenerateness, or maybe let's just write, you can make a symplectic form out of it. So this is basically first part of the remarks. However, I wanted to say, maybe we can just add this real situation. So real situation means the Lagrangian of the theory, as you have seen it yesterday. Real situation is really just non-smooth, not smooth. And this is why I personally also prefer this, to present this like non-smooth part. Also, the smooth part gets quite complicated because you have this topology of this Frichet manifold and things like that. Okay, and then last bit for this part of the lecture is just to say that, and then I will have some time for questions, and then we'll see what else we can do. And so that we call this whole situation this. So this means basically linearized field equations and having this conserved symplectic form. So maybe just, again, a little remark for understanding. So this really means, so I mean, it's just not, it doesn't mean that you have something arbitrary in the background, but it really means we have assumed the linearized field equations. So this thing here is conserved under evolution of the linearized field equations, right? That's the sort of the spirit of this. So I have a chat here, and I consider the evolution of that chat with respect to the linearized field equations. And then maybe I can write it like this: symplectic form conserved under conserved, oops. So those two things, we call this Hamiltonian time evolution. But this is more like this name is sort of like we choose this name because it's a loose metaphor for the situation in classical mechanics, where you have a Hamiltonian function, and this gives you a Hamiltonian vector field, and this gives you Hamiltonian flow. So this would maybe be something like those linearized field equations, and you have a symplectic form. It's just a loose analogy, but this name is just what we refer to it. Okay, and that's all I wanted to say for this part. And like now, we'll just take some minutes to talk about questions, and then I will tell you a little bit more about other conserved quantities. So there's one conserved quantity, or one quantity which is sometimes conserved, which we will need to later tonight and tomorrow. I'll just write that down, and then we'll talk a little bit, if there's time, about symmetries. But now the question would be, first of all, what questions do you have? And is this sort of clear, this picture, or plausible or not so plausible? And like, you're also invited to be critical.
So in general, for symplectic form, the manifold should not be compact?
No, it doesn't have to be. Yeah, so as far as I know, it doesn't have to be compact. So in our case, it's more, yeah. So in this case, it's more important because in this case, if the manifold is compact, like sort of this conserved quantity here will really vanish. So here it's really essential that the manifold is non-compact. But for example, Minkowski space is non-compact, so like many manifolds.
It's somehow bizarre because generally in physics, conserved quantity are related to some symmetry.
And in fact,
this is come from anti-symmetry.
so there's two things. So in fact, like what I wanted to say later, that's really how we started when we first found this conserved, like the surface layer integrals. We really considered symmetries. We wanted to sort of see what is a generalization of Noether theorems to this setting. That's when those surface layer integrals came up. And in this case, and I'll explain that in a minute. And this is just in this case, but you're right, the symplectic form you anti-symmetrize in the chats. But this is a symmetry is not the opposite of anti-symmetrizing. Here, anti-symmetrizing just means taking UV minus VU. A symmetry is something more general. I'll write it down later, also in normal physics. There are conserved quantities which come from symmetries, and there are some which don't. Felix, you want to add something? Or? No. Yes. Yeah. Are there any other questions about this, or do you feel sort of semi-comfortable with it so far? Or, it's quite new and quite different. And as I said, Felix will say more about the connections to physics you know tonight. That's what I mean. Yeah, the next lecture. For me, the day ends at lunch because I'm finished. Yeah. Okay, so maybe if not, so we've talked about symmetries. So I thought the two things which would still be nice to say would, first of all, one example of how the symmetries relate to conserved quantities, and then there's one other theorem which we need for the next lecture. Also, there exist more, so maybe let's say, there are more conserved quantities. For example, first example would be Noether-like theorems. And this is basically what Felix and I have published in 2015, if you want to check it out on the archive. Okay, so they basically establish a connection as usual, between symmetries and conserved quantities. And so I should say, though, the reason why this might be interesting is because it tells you a little bit about how we usually think about the theory. Okay, so a symmetry is, like it turns out, I should say, is a mapping phi. That's the letter we usually use for symmetry. Phi, which basically takes some parameter range. So for example, let's just call it minus tau max to tau max times space-time to f. So what this basically does is pushes around your space-time in f. And we also need to assume for which the combination of taking the little function L we had before after phi, and so this is a mapping from tau max minus tau max times m to r. So basically, I just carry out L after this, so it's just a composition. For which this combination here is continuous and d tau, so the derivative of this respect to tau, L after phi, exists and is continuous as well. Okay, so this is basically what a symmetry is, or basically what the, okay, so I should say it like this, and of course there's more conditions on which type of symmetries you have. For example, you can say def a symmetry of the Lagrangian. Maybe I could have said this is a variation, a symmetry of the Lagrangian. This is what we define now. So let me just write it like this. A symmetry of the Lagrangian is phi tau as above, such that the following holds, such that L of x phi tau of y is the same thing as L of phi minus tau of x comma y, and this is supposed to hold for all x, y in M, and for all tau. Okay, this is the definition of a symmetry of the Lagrangian, and I'm just going to write down the corresponding theorem. So then it follows, I mean, we called it a theorem, but it's really simple to prove, and in fact we put it in one of the exercises for tonight if you want to, so it's like a couple of lines. The difficult part was more to really find this sort of formulation in terms of conserved surface layer integrals. Okay, so let rho be a minimizing measure. And phi tau a symmetry of the Lagrangian. Okay. Then for any compact subset, omega of M or F, it doesn't really matter, we have the following quantity, vanishes. And so this is the derivative with respect to tau of the integration with respect to omega, d rho of x, with respect to M without omega, d rho of y. And then the quantity is basically L of phi tau of x y minus L of phi minus tau of x y. And this integration here, I should say, the derivative at tau equals to 0. And this is 0. Okay, so you see again, so we have the derivatives outside because the assumptions of this paper do not necessarily allow you to pull it in, but let's assume you can pull it in. And then you see again, it has the same structure as the conserved quantity we have found before. So this is a phi tau, and this is a phi minus tau. Okay, and as I said, the proof of this is not very complicated. So you could, for example, do it later tonight in the exercises if you want. And in fact, this really yields current conservation and conservation of energy momentum. Of in the limit. So this is also in this paper in 2015, and so this is sort of an indication that those structures, those surface layer integrals, really seem to be the good notion to work with. In the same spirit as like yesterday during the exercises, we've talked about there are reasons for those definitions Felix has shown you, and in a similar spirit here, you could say those seem to be the right structures to work with. Okay, and so there's one more thing I wanted to say, and then we're already done. Yep.
Should there be x and y switched in the second Lagrangian way?
No, here.
Well, I mean, you have twice the same expression.
No, this is tau and this is minus tau. That's important. Yeah. And this you see also already, like this is also a little bit related to sort of, yeah. So maybe I should write this in yellow. So this is tau, and this is minus tau. Okay. And so more importantly, maybe for us, is the following theorem. And so that's written in Felix and me have done just recently. And so I need to use one expression which I have not defined so far, and which also I felt is a little bit too much for now. You'll learn it tomorrow. And so I'll just say it like here. So there's an expression which looks like this: S delta 2. I think we wrote it like this: U V. So this part here is something which we call a nonlinear correction term. So it'll pop up tomorrow. And this here is something which is like a Green's operator. For the linearized field equations. But again, I will not define it here because it would lead maybe a little bit too far. And using this, we have the following theorem. So let me write it over here because it's the last thing I wanted to say. So we have the following theorem. Okay, given a compact set, as always, omega subset M, if two regularity assumptions are satisfied, so you can find them in the paper. The symmetric bilinear form like this. So it has a comma, as we learned yesterday, because it's for real quantities. So this symmetric bilinear form takes two elements of J lin cap J test. And gives me a real number. And it is defined as follows. So it takes U and V. Oh, and there's an omega here to indicate that basically we're considering the area omega. Now, first of all, I have the same thing as always if I have a conserved surface layer integral. So I have the integration over omega with respect to rho, and the integration over m without omega with respect to rho and y. And then the quantity which I integrate is a little bit more complicated. So first of all, I take the chat derivative in the direction u, acting on the first argument, and in the direction v, acting on the first argument. And I subtract from that the chat derivative acting like in the direction of u on the second argument times the chat derivative in the direction of v on the second argument. Okay, so far so good. But now there's two more terms involving those nonlinear correction terms. Now first I add 2 times this, nabla 1, and now s nabla 2 u and v. So this is just this nonlinear correction term acting on the first argument of the Lagrangian, minus 2, and now I have the same thing acting on the second argument of the Lagrangian. Okay, so I close the bracket, I put L of xy here, and this is the definition of this symmetric form. You see it's symmetric under exchange of x and y, and this delta 2 is also symmetric. You'll see that tomorrow. But you see it in those terms, that it's symmetric. And now this satisfies the following relation. This satisfies nabla u, v, omega. And now it's not 0 in general, but in general there's sort of a volume term. So this is the same as the integration over omega for nabla 1u nabla 1v times nu half. So acting on a constant. So this means, for example, the derivative part in here doesn't show up, but the derivative part in here does also not show up because both of them. So this is the notation we use. If there's 2 ones, they both act on a constant. I can write down what this term is later. Plus, and now I have the derivative s nabla 2 of u v times nu. And then this whole thing integrated with respect to d rho of x. Yeah. So there's an x dependent in those terms. And so in fact, so if I choose u and v with notation as before, so this would really be something times a of x, b of x times nu half. And this would be something like the scalar component of this nonlinear correction term. Okay, so this is like basically what I wanted to say. This is the quantity we find. So in general, it's not 0, but it is 0. So I'll just write this here. I hope you can see this. Maybe make a big arrow here. That's what I meant, yeah. Yeah. So this is in general, this is not conserved. However, so like maybe I put it like this. Conserved if the following things hold. If U does not have a scalar component, or V does not have a scalar component. Okay, then the first term would vanish because either A or B are 0. And if this S2 delta 2 of U, V also does not have a scalar component. So we'll just write it 0 omega for some omega. Okay. Yeah, that's it. And that's all I wanted to say. So it depends on omega, yes, and therefore also on the. So omega doesn't, like, omega is a subset of a space. So it could be a vector space, but it doesn't have to be. So in this case, I would say it's not important that omega has. Yeah, because the role of omega here is different. It's like, it's not a symplectic form on omega. It's just a symplectic form dependent on omega. Yeah. Sorry? Maybe you could call it like this, yeah. Yeah?
What is S2 delta 2 of the commutator?
So that's what I said. This is this non. Oh, that's not the commutator. It's just delta 2 is a function. It has 2 arguments. Yeah. Oh, next S, sorry. Yeah, in fact, so this 2, so here I didn't introduce this. So this thing is a Green's operator, and this comes from a perturbation expansion, which Felix will explain a little bit on Thursday.
That's okay, but
Yeah, and
yeah,
yeah, it should be the same, but the reason, like, so you have some freedom in choosing them at different orders. That's why I copied it wrongly. So, but it's really the same thing as here, yeah. Yeah. Mm-hmm.
There is maybe sub-manifold of n. The symplectic form is 0. So there is no conserved quantity on this sub-manifold that the symplectic form 0 is.
Maybe it could be. So in general, like, M is not a manifold. So it could also be that, like, if M is a manifold, you could consider submanifolds. And then, like, okay, it could very well be that you pick an omega, a submanifold, so that the symplectic form vanishes, yes.
But there is no conserved related to some conserved quantity.
So at least I would say no, yeah, right now. Yeah.
By this method of continuous changing of Lagrangian, we get just continuous symmetry, not quantum symmetry, like a discrete symmetry.
So maybe I would refer this question to Felix's lectures about quantum space terms on Thursday. But in general, like this, yeah, this description is sort of, depends a little bit, like it depends what you call classical. And this.
Classic symmetry depends on a continuous parameter.
So, okay, so in this sense, this depends on a continuous parameter, yes. Yeah.
We don't have a continuous parameter.
Mm.
Have two eigenvalues.
Okay, but let me say it like this. Like this really gives conservation of charge in the limit. Yeah. Yeah, exactly. We'll learn more about this in the afternoon. Okay. Are there any other questions? Okay, otherwise, thanks very much. And in the afternoon, Felix will take over again.